All right, let's dive right into this explainer. Today, we're unpacking a concept that is an absolute game changer for future-proofing how you debug your systems. We're talking about transforming your observability data into arbitrarily wide events. Now, if you've been around the block in software development, you are probably intimately familiar with the legacy three pillars model, where metrics, logs, and traces all live in these completely separate, totally disconnected silos. And honestly, you know exactly how frustrating it is to constantly switch contexts during a high-stress outage. It's like you see a massive spike on a metric dashboard, and then you frantically pivot over to your logging tool, writing these complex queries hoping to catch the exact error that caused the spike, only to realize, wait, I actually need a trace to figure out the real request path. It's exhausting. So, based on Chapter 6 of the book Observability Engineering, titled Making Structured Events Arbitrarily Wide, we are going to explore a radically different approach. We're going to learn how to collapse those arbitrary boundaries completely, empowering your team to ask literally any novel question of your systems long after the code is actually shipped. Here is how we're going to break this down today. First, we'll unpack the core concept of arbitrarily wide events. Then, we'll look at injecting service and code context, connecting that data to your users and errors, exploring performance and edge cases, and finally, we'll wrap up with a really standard filtering convention to cut through the noise. Okay, moving right into Section 1, the arbitrarily wide concept. So, what does it actually mean for an event to be arbitrarily wide? Listen, this isn't just about hastily slapping a few extra tags onto your logs. It's a fundamental shift in how we capture system state. The absolute crucial point here is that there is practically no limit to the context you can stuff into one of these events. In a unified observability system, you should be packing your events with as much data as you think you might someday need. You never know when it's going to come in handy. In practice, this means capturing data with both high dimensionality and high cardinality. And what does that mean? Well, high dimensionality simply means having lots of different attributes or keys. Maybe you start with 10, but pretty soon you have 50 or even 100 different pieces of context. High cardinality means those attributes can have millions or literally billions of unique values. Think individual user IDs, trace IDs, shopping cart IDs, the whole shebang. Legacy systems would completely fall over if you tried to index a billion unique user IDs. But modern observability systems built for arbitrarily wide events, they are specifically engineered to handle exactly that kind of load. To make this concrete, think about what a typical JSON span for a shopping cart service looks like when it's structured this way. It's not just some basic timestamp and a generic, unhelpful text message saying, user added item to cart. No way. It is packed with incredibly rich context. You've got HTTP routing data, unique identifiers like a user ID and an order ID, and actual business logic like the exact number of items in that cart. But it doesn't stop there. You also have infrastructure details. We're talking in the AWS region, the availability zone, and the specific build ID. All of this lives right there in one single record. When an incident inevitably occurs, you don't have to guess what the state of the world was when that event fired, because the event itself remembers the complete state of its universe. The beauty of this approach is that it completely eliminates the need for expensive, complex database joins later on. Why? Because everything you could possibly need is already right there in the event payload. Seriously, think back to the traditional nightmare of trying to join an aggregated CPU metric table with a completely unstructured application log table in the middle of a Severity 1 outage. It's slow, it's incredibly error-prone, and honestly, a lot of times it's just downright impossible. By making your events arbitrarily wide, you completely remove the historical limitations of those old siloed tools. Your immediate questions, not your data model's past constraints, are what actually set the boundaries of what you can learn during an investigation. So, you're probably wondering, how do we actually construct this ultimate evidence board from the ground up? Because we all know the default server logs aren't going to save you when the pager goes off at 3 a.m. Let's look at the layers we need to add. Which brings us to Section 2, Service and Code Context. The very first layer of our cake here is giving the event fundamental self-awareness. When things break, and they always do, the first question is almost always, whose code is this, and what environment is it running in? By injecting these foundational service attributes right into the event, you immediately know exactly who owns the system and who to page. Imagine looking at a massive latency anomaly and instantly seeing that the checkout team owns this microservice. And hey, their on-call Slack channel is right there, #checkout_alerts. You don't have to go digging around in a dusty internal wiki page that hasn't been updated in 6 months just to figure out who to wake up. Sophisticated orgs will actually tie these attributes directly into their internal service catalog via their deployment pipelines. That ensures the ownership data riding along on every single event is always perfectly accurate. There's a stark contrast here that's absolutely crucial to understand. Instead of the slow guesswork of legacy methods, you have exact build information instantly available. Let's say you just shipped a new feature using a canary deployment, and you're getting kind of worried about some intermittent performance degradation. You absolutely do not want to hunt through deployment dashboards trying to correlate timestamps with error spikes. It's a waste of time. If you've attached your build ID, your feature flags, and your dependency.version directly to your wide events, you can instantly group your performance data by those exact attributes. You can see clear as day that the latency spike is entirely isolated to build version 2.4, while version 2.3 is purring along perfectly fine. The events literally answer the question for you. But to truly understand execution flow, we need to trace the narrative of the work. That means logging the route, the time it took, and its exact place in your distributed system. Telemetry about request and execution flow is what turns a totally isolated log line into a coherent story with a beginning, a middle, and an end. When a user submits a support ticket saying, hey, the checkout page is slow, well, that's pretty vague, right? But with execution context, you have the absolute fastest way to go from that vague complaint to a precise diagnosis. You can prove that a specific post request to the /cart/checkout route was slow, specifically because a downstream database call held things up for exactly 142.5 milliseconds. And when you bring distributed tracing into the mix, things get really powerful. Now, distributed tracing can sound intimidating to set up, but fundamentally, tracing is really just fancy logs combined with passing some unique IDs around in HTTP headers. By including the trace ID, the span ID, and the parent ID right in the event payload, this single JSON object knows exactly where it fits into the broader distributed architecture. It knows exactly who called it, and it knows exactly who it called next. It effectively builds this connective tissue across your entire microservice fleet. So we have the system context, but how do we know exactly who is experiencing the error during one of these latency spikes? Let's move to Section 3, Users, Errors, and Impact. We have to connect these back-end failures to actual human impact. Because let's be real, an error that affects 0 users is just a log line, but one hitting your biggest customer, that's a massive emergency. Embedding specific error details directly into your event allows you to instantly pinpoint the failure mechanism without digging through separate, messy text logs. I personally absolutely love the distinction here between the error type and the error slug. The error type is fantastic because it lets you filter out internet background noise. You know, like some automated scanner bot trying to hit a PHP admin URL that doesn't even exist on your node server. And the error slug, that gives you a unique, greppable string identifier. You literally just copy the slug, paste it into your IDE search bar, and boom, you are immediately staring at the exact line of code that triggered the failure. 0 guesswork. Now, adding user attributes is what lets you slice the data to see if a bug is hitting those free tier accounts or your most lucrative enterprise clients. Understanding exactly which users are experiencing a problem is usually the very first question incident responders get asked by management. By appending the user ID, the user tenant, and the user type directly onto the event, you immediately link system behavior to business impact. If you run a multi-tenant B2B application, a bug might only trigger when a specific tenant's massive dataset is queried. Without that tenant attribute on the event, you're just staring at a sea of intermittent 500 errors, completely lost. With it, you instantly see that 100% of the failures belong to Acme Corp. This right here highlights exactly why high cardinality is a superpower and absolutely not a problem to be engineered away. Legacy metric systems forced us to drop unique identifiers like user IDs simply because their time series databases couldn't handle the cardinality explosion. But a single massive enterprise user's traffic pattern looks vastly different from a casual user's pattern. When you average them together into one metric, you completely lose the signal. With arbitrarily wide events, you retain all of that granular detail, empowering you to query exactly how your most important revenue-generating customers are experiencing your platform at any given microsecond. Let's check out Section 4, Performance and Edge Cases. So how does this build when we account for specific application behaviors, limits, and all those weird edge cases that cause the most painful bugs? Tracking cache hits, feature flags, and localization settings can instantly highlight really obscure bugs tied to specific user configurations. Think about how incredibly hard it is to debug an issue that only occurs for users whose browser language direction is right to left, who are trying to pay in Canadian dollars, while simultaneously being bucketed into the B variant of a brand new checkout feature flag. It's a nightmare. If those specific dimensions aren't attached to your events as they occur, you are flying totally blind. You'll never reproduce that locally. But wide events, they will surface that exact pattern for you immediately. And consider API quotas. If a user's behavior suddenly changes and they exhaust their quota, having these rate limit attributes attached to the event clarifies the situation right away. You don't have to sit there wondering if there's a performance bug in your code or if a customer's automated script just went rogue in a tight loop and ate their entire API allowance in 3 minutes. The event tells you exactly what the mathematical limit was, what the cost of the query was, and how much quota they had remaining at the exact moment of the failure. It takes a complete mystery and turns it into an open-end shut case. You can also analyze operational context, like memory and CPU usage, alongside request duration, to isolate exactly which host is failing. This perfectly solves the classic noisy neighbor problem. By tagging hardware metric data directly onto the application's structured events, you can clearly see if elevated response times correlate directly with memory usage maxing out on, say, just 2 specific instances in the cluster, while the rest of the fleet is totally fine. You have the full context to see exactly what heavy workloads were running on those specific instances when the memory spiked. You aren't guessing if the CPU spike caused the latency. The combined event data definitively proves they happened to the exact same request simultaneously.
Let's wrap up with Section 5, the filtering convention.
Okay, so with all this incredible, rich data flowing in, we obviously need a standard way to find the needle in the haystack. By tagging your most important high-level wide events with a simple attribute, something like main equals true, you can quickly query the overarching work a system does without getting completely lost in granular subspans. For instance, you might have a single trace that generates 50 tiny individual database query spans, a dozen cache check spans, and an authorization span. If you're trying to figure out your P99 latency for the checkout endpoint, looking at all those tiny subspans will totally skew your data. Filtering for main equals true gives you that top-level summary of the overarching HTTP request instantly, ensuring your calculations are accurate while still keeping all that granular subspan data available if you need to dig deeper into a specific bottleneck. And a modern observability tool can take all those hundreds of attributes we just talked about and do the heavy analytical lifting for you. When it compares successful events against failed events across, say, 63 different dimensions, instantly, it's magical. It might immediately surface that 98% of your failed requests share a single specific attribute. They are all running in the US East 1A availability zone. No human could manually pivot through 63 different attributes fast enough to find that correlation during a stressful outage. But because we captured arbitrarily wide events with high dimensionality, the tool can calculate those statistical differences and find the exact source of the pain point in literal seconds. So here is the big takeaway. If you rely on pre-aggregated metrics, you are permanently destroying your future investigative options. The moment you average data into a time series bucket, you lose the ability to ask why or for whom. It is a one-way street where context is discarded forever. But by building arbitrarily wide structured events, you retain the high cardinality details that make every single request unique. You unlock the true voice of your systems, allowing you to derive any metric, trace any flow, and answer completely novel questions on the fly that you couldn't have possibly predicted when you wrote the code. So I leave you with this. What crucial piece of context is missing from your system's events right now, and what's stopping you from adding it today?